Hello viewer and welcome to the e-learning classroom. So today we'll be looking at this practical. So we have the ammeter, we have the voltmeter here, cells, we have a switch, and then we have nichrome wire. So we'll be filling this table for length, PD or voltage, current, resistance, which is given by PD over current, and then reciprocal of current. Then from there we'll plot a graph of reciprocal of current against resistance R, and then we'll determine the slope of the graph. And then given this equation, EMF equals IR plus IR, we'll be able to determine the value of EMF and also the value of internal resistance. So first of all, we arrange the apparatus as they appear. So we have the cells. Maybe I can put the cells. Let me input the cells we have here. So I have the cell here. So the cells are here. From the cells we have the ammeter somewhere here close to the cells. We have the ammeter here close to the cells. Then we have nichrome wire here, somewhere here. Nichrome wire. And then from there we have a voltmeter below the nichrome wire. So below the nichrome wire we have a voltmeter, and then we have a switch on the side of the cells. So on the side of the cells we have a switch. So that is how the apparatus are arranged in the equation. So we start with the connection. So for the connection we start from positive terminal. So from positive terminal we have a wire. From positive a wire. And this wire goes straight to the ammeter. This wire goes straight to the ammeter, so we connect to the positive because we are starting from positive. Then from the ammeter, we have a wire. From the ammeter, we have a single wire going straight to the nichrome. So from negative of the ammeter, a wire going straight to nichrome at 0. Straight to nichrome at 0 there. Straight to the nichrome. We also have another wire coming from the wire at nichrome. Another wire coming from there. And this one goes straight to the voltmeter. So because we are in the positive, we connect still at positive. We can work with the scale of 0 to 5. 0 to 5. And then from there, we have another wire from negative terminal. We are now done with the positive. So one wire from negative terminal goes straight to the switch. From negative terminal, the wire goes straight to the switch. From negative straight to the switch. And then from switch straight to the nichrome. So from the switch straight to the nichrome. Maybe we can use a longer wire for that. From switch here straight to the nichrome. For the nichrome, because we are starting with 10, maybe we can put it at 15. We'll adjust. Straight to the nichrome. Then we have one more wire, the last one, which is connecting. So the last wire is connecting voltmeter. The last wire is connecting voltmeter to the wire at nichrome. So from negative is connecting this wire at the nichrome. So this wire is connecting the one at the nichrome. So that is how our setup looks like. Yeah, already you can see both the ammeter and voltmeter are giving some reading. Maybe we can disconnect the switch so that we safeguard ourselves. But you realize both the ammeter and voltmeter are already giving some reading. So what we do now, because we are going to fill the table, first voltage and current, that is the one we fill now first. So what we do, the first thing is that, the first thing we are going to do is start from 10. From 10, remember for the ammeter, we are using scale of 0 to 1, the upper scale, voltmeter 0 to 5, which is the lower scale. So let's start at 10. We take the readings of both the voltmeter and the ammeter. Both the ammeter and so let's see at 10. At 10, what we adjust to 10, then we close the switch. So viewers, we are working with a scale of 0 to 1 for the ammeter, and for the voltmeter, we are working with a scale of 0 to 5 for the sake of the values you'll be getting. So maybe we can close the switch at a length of 0.1 and take the readings. So let's see. So at 0.1, let's see the values we have for the voltmeter and the ammeter. So this, for the ammeter, these are 32. So we have 32 times 0.02, which gives us 0.64. 0.64, as you can see from there. So that is for the ammeter, 0.64. Then for the voltmeter, this one gives us 0.1. 0.1. No, actually it's 1.0, sorry. It's 1.0 because we are working with the lower scale. So from there we go to 20. We adjust this to 20. Observe the ammeter and voltmeter. So we have it at 20 there. So for the voltmeter, we have 1.5. 1.5. Then for the ammeter, we have, these are 25. So 25 times 0.02. This is 0.5. No, this is 0.50. Then we go to 40. We go to 40. Straight to 40. Let's see. Forty is somewhere there. So for the voltmeter, we have 2.0. 2.0. Clearly. Then for the ammeter, these ones are 17. So 17 times 0.02, this is 0.34. 0.34. Then we go to 50. We go straight to 50. So we have 50 there. So for the voltmeter, I don't know why that shifted. We were at 40. You are now at 50. So let's check again at 40. So for the voltmeter at 40, we seems to have 1.9. Sorry, this is 1.9. Sorry for that. Let's correct that. It's 1.9. Maybe you can correct that. This one is 1.9. 1.9, sorry for that error. Then for the ammeter, the reading is these ones are the ammeter is still okay. So we go to 50. So for the voltmeter, this is 1.0. 2.0, sorry, 2.0. 2.0. Then for the ammeter, these ones are 14. So 14 times 0.02, this is 0.28. 0.28. We go to 60. We go straight to 60. So for the voltmeter, this one is 2.1. 2.1. Then for the ammeter, we have 13. So 13 times 0.02, this is 0.26. 0.26. We go to 70 straight. So we go to 70. For the voltmeter, we have 2.2. 2.2. Then for the ammeter, these ones are 11. So 11 times 0.02. 11 times 0.02. This is 0.22. 0.22. We go to 80. We go to 80. So at 80, for the voltmeter, we have 2.3. 2.3. Then for the ammeter, these ones are 9. So 9 times 0.02, this is 0.18. 0.18. Then lastly, we go to 1 meter. So we extend all the way to 100, which is 1 meter. We extend all the way to 100. So for the voltmeter, we have 2.4. Let's confirm. This one is 2.4. 2.4. Then for the ammeter, these ones are 8. So we have 8. 8 times 0.02, which is 0.16. 0.16. Those are the readings we have now. Those are the readings we have. You can observe the ammeter and voltmeter readings as we go back. Observe the ammeter and voltmeter readings. Let's see, dear viewers, so that you understand. Observe the ammeter and voltmeter readings. Observe the ammeter and voltmeter readings. So, and that is how now we are able to get the values. So we'll be using these values later. We'll be using these values to plot a graph. So viewers, we want to plot a graph of 1 over current against the resistance. So what we do, first we draw the axis. We start by drawing the axis. So we draw the axis, the two axes. We have the two axes, so we are drawing them here. The two axes. So viewers, we have the two axes now. Each one must have an arrow. Then since we are plotting a graph of one reciprocal of current of resistance, so we can label this side 1 all over current. You label the quantity and the unit. The unit is per ampere. Then this side we label it resistance. The unit is ohm. We are labeling quantity and unit. Then from there we consider for the resistance. Maybe you can first fill the values of resistance. So resistance is voltage over current. 1 divided by 0.64. This one gives us 1.563. Then we have 1.5 divided by 0.50. This one is 3. Maybe we can say 0.000. 1.9 divided by 0.34. This one gives us 5.588. 2.0, 2 divided by 0.28, 7.143. Then we have 2.1 divided by 0.26. This is 8.077. Then 2.2 divided by 0.22, 10.00. 2.3 divided by 0.18, 12.78. Then lastly 2.4 divided by 0.16. That is 15. Maybe you can say 0.00. This one must have at least 4 significant figures. Then reciprocal of current. 1 divided by 0.64. 1.56. 1.563. 1 divided by 1 divided by 0.5, 2, maybe 0.000. Then we can have 1 divided by 0.34, 2.9, 2.912. Then we have 1 divided by 0.28, 3.57, 3.571. 1 divided by 0.26, 3.8, 3.846, 3.846. Then we have 1 divided by 0.22, 4.5, 4.545. Then 1 divided by 0.18, 5.5 recurring, so 5.556. Then 1 divided by 0.16, 6.250. So that is the full table now. That is the full table. Then we are plotting a graph of reciprocal of current against resistance. We are plotting a graph of reciprocal of current against resistance. So let's see. For the reciprocal of current, the largest value is 6. Smallest is 1.5. Largest is 6. That is for the reciprocal of current. So maybe you can work with the 2 squares to represent 1. So 2 squares, 1, 2, 3, 4, 5, 6, 7, 8, maybe up to 9. Then for the resistance, smallest is 1.5, largest is 15. Let's see how many squares we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's say we can work with 2 squares, 2, 4, 6, 8, 10, 12, 14, 16. We have that, and then from there we can now we have for the resistance, maybe we can have a small table for our values so that we can easily plot them. So let's say we have a small table for our values. We have 1, 2, 3, 4, 5, 6, 7, 8. These are 8 values. So let's see. One, 2, 3, 4, 5, 6, 7, 8. So we have 8 values. So for this side we have let's say we have reciprocal of current, 1 over current, and then we have resistance. For the reciprocal of current, our accuracy is 0.1 because we have 10 divisions 1, but for the resistance, our accuracy is 0.2. This is per ampere, this is ohm, because you have 10 divisions 2. So let's see now what we have here. Let's start with the reciprocal of current. So this one will be 6.4 squares because we just say this one will be 15.63, sorry, because we have 1.563 divided by each small square is 0.1, so we get 15.63. Those are 15.6 squares, 20 squares, 29 squares, 0.1 of course, 29.1, 35.7 squares, 38.5 squares, 45.5 squares, 55.6 squares, last three, 62.5 squares. These are the number of small squares or divisions. Then for the resistance, we have, let's see, for the resistance we have 1.563 divided by 0.2. These are 7.8 squares. 7.8 squares. Then we have 3 divided by 0.2. 15 squares. 5.588 divided by 0.2, 27.9 squares. 27.9 squares. Then we have 7.143 divided by 0.2, 35.7 squares. 35.7 squares. Then we have the fifth one, 1, 2, 3, 4. The fifth one, 8.077. 8.077 divided by 0.2, which is the accuracy of our scale. These are 40.3. This 40.4 squares. 40.4 squares. Then we have 10 divided by 0.2, 50 squares. Then we have 12.78 divided by 0.2, 63.9 squares. Then lastly 15 divided by 0.2, these are 75 squares. So these are the number of squares we have. It's good to understand that we are basing on our accuracy here, because we are saying 10 divisions 0.2, so each division is 0.2. 10 divisions is 2 here, so each division is 0.2. That's why we are taking for the resistance, each value of resistance we divide by 0.2 to know how many small divisions will be here. Then for the reciprocal of current, 10 divisions is 1, so each division is 0.1. So that's why for reciprocal of current, each value we divided by 0.1 to know how many divisions. So from there now we can plot those values. So we can plot those values in our table from the graph. Let's start with the resistance. We go 15 horizontally and then vertically. 15 horizontally, then 7.8 horizontally. That's 7 squares. Then we raise 15. So this is 7.8 here. Then 15.6 somewhere there. Then we go 15 squares. We raise 20, 10, 20 there. We go, that is 15, 20, 27. This is 10, 10, 20, 27 here. 27. Then we rise 29. 10, 20, 29. And this is 27.9, so somewhere here, somewhere there. Then we go 35. So we have 10, 20, 30, 35. We rise 35. So 35 we rise 10, 20, 30, 35. So somewhere here. 40.4, so 10, 20, 30, 40, then we rise 38, 10, 20, 30, 38 here, 38.5, then 40.4, so somewhere there, 50, 10, 20, 30, 40, 50, 50 we rise 45, 10, 20, 30, 40, 45.5, 45.5 there, then 63.9, 63, 10, 20, 30, 40, 50, 60, 63 is here, we rise 56, 55. So 63 rise 55. 10, 20, 30, 40, 50, 55, so 55.6, 55, somewhere there, then 75. So we have 10, 20, 30, 40, 50, 60, 70, 75. We raise 62. 10, 20, 30, 40, 50, 60, 61, 62 and a half, 62 and a half is there. So these are the values we have now for our graph. So line of best fit, now, let's see. Line of best fit. There. So we have our line of best fit, dear viewers. We have our line of best fit there. So that is a graph of reciprocal of current against the resistance. Then we are taught to find the slope of the graph. So the slope of the graph, maybe we can pick any two readable points to find the slope. So maybe we can take this point here, and then the other readable point. Maybe we can take the other readable point. Maybe we can take this point here. So let's see. These are our two readable points. We mark the points. We mark those points so that we read the values there. So we mark those points like that. So we can have this, the readings here and the readings here. So this one is 4.0. Then this one is 2.4. 2.4. Then this side we have, so this is 8. These are, let's see, 10, 20, 30, 40, 47. So 47 times 0.2. This is 9.4. 9.4. Then on the upper side we have 4.3. 4.3. So these are the values we have. Then from there we are told to determine the slope of the graph. The slope of this graph. So maybe we can solve it from here. The slope of this graph. So we know slope is given by changing reciprocal of current divided by changing resistance. So change in the reciprocal of current is a change in y. If a graph has right hand above left hand, the graph is as a positive slope. So that means this one over this, the change in reciprocal of current divided by change in resistance will be 4.3 minus 2.4 divided by 9.4 minus 4.0. So let's see. 4.3 minus 2.4, we get the answer. Then divided by, into bracket, 9.4 minus 4.0, close the bracket. So this one gives us 0.35. 0.3519. Let's repeat again. Maybe confirm. 4.3 minus 2.4, cross the bracket, divided by, into bracket, 9.4 minus 4.0. So this one gives us 0.3519. We need to know the value of the slope. So this is per ampere per ohm, because we have per ampere on the numerator and per ohm on the denominator. So that means the unit here will be per ampere per ohm. Per ampere per ohm. And then from there, we are given this equation, and then we are told to determine the internal resistance and also the EMF. So what we do, first we can multiply through by, so we can simplify this equation. Let's say we can do rough work on this side. We can do some rough work here. So we have EMF is equal to IR plus IR. So multiply through by 1 over IE. Multiplying through by 1 over IE. So on this side we'll have 1 all over I is equal to, when you multiply this by 1 over IE, you will cancel, so you remain with 1 over I is equal to R all over E plus R all over E. So when you multiply through by 1 over IE, you get this equation. And this equation is in the form of Y is equal to mx plus c. Because 1 over I is the y-axis, this one here. Then R is the x-axis, this one here. So, and that means slope represents, so slope represents 1 over EMF, because essentially R of 1 over E times R is the same as mx, where x is the R. So 1 over E times R. So we are saying slope represents 1 over E, and that means EMF is equal to 1 over slope. If you find the reciprocal both sides, so it is 1 over slope, so 1 all over 0.3519. So, and that gives you EMF to be, so let's see, 1 divided by 0.3519. This gives you 2.842 2.842, and because it is EMF, it must be in volts. This one must be in volts. So this one will be in volts because it is a EMF, or the electromotive force. Then we have the internal resistance. So if you look at the interpretation here, R over E is the intercept, the reciprocal of current intercept, because it is C represents the intercept, and that means we read the intercept here, because this one is Y intercept, whereby in our case we call it 1 over I intercept. So we can say R all over E is equal to 1 all over current intercept. So, and that means R divided by, of course we found the EMF is 2.842 is equal to, the intercept here is 1. So, and then we can find reciprocal, we can multiply. So, and that means the R becomes, if you multiply, you still get 2.842 ohm. 2.842 ohm. That becomes the value of the internal resistance. I hope you're able to see this, dear viewer. So that is how we solve the equations given, applying the knowledge we have.